Can you hear me? Awesome, good. Right, so my name's Liz. I work for a company called Aqua Security. We help enterprises with container security. And one of the things that you want to do when you're trying to secure something is have secure connections between components. So I felt like secure connections is something I really kind of should understand. If you are a consumer, there's actually a pretty good user experience around getting a secure connection. This is some kind of bank, apparently, and they have this sort of advice about making sure you've got your green padlock. So, you know, people like my mum can probably set up secure connections. That's okay. For people who work in technology and for people who are programming and for people who are dealing with infrastructure components, the user experience is not quite so good. So, for example, anybody here using Kubernetes? Few of you. Keep your hand up if you've ever worked through Kelsey's Kubernetes the hard way. Couple of hands, yeah. It's a very, very good way of learning about what Kubernetes is, and it includes this whole section on setting up certificates and certificate authorities. And it takes over 400 lines of instructions to explain that. And this isn't a criticism of Kelsey, and it's not a criticism of Kubernetes. It's just the fact that setting up these certificates and keys and certificate authorities can get really quite confusing and verbose, and I'm not going to ask for a show of hands, but I am certainly prepared to admit getting myself very confused, dealing with different key files and certificates and going, what the hell is all this about? So what I'm going to try and do this evening is explain what's going on with when we try to secure a connection, explain some of the common error messages that you might well come across, and hopefully leave you in a position where you won't be like me with all these like different files going like, what the hell are these things? Okay, so the basics. Suppose I want to have a transaction with Monzo, for example, and one of the things we need in our communications is the establishment of identity. I want to know that I am actually talking to my bank and not some random person on the internet who I'm about to give money to. And we also want to encrypt traffic between us so that if somebody is listening in, they can't, well, intercept the messages, maybe read information, or possibly even manipulate the message. If I send $500 to my bank, I want to know that $500 get there, not 400 because somebody man in the middle did. So we have these two key things we're looking for from a secure connection: the establishment of identity and then encryption between those two parties. We might be talking about HTTP traffic, and for the purposes of this talk, I will talk about HTTP traffic. Could be other protocols, but we use HTTP a lot, right? HTTP in its secure form is called HTTPS. I sort of grew up believing that stood for HTTP over SSL. I think it's been sort of slightly manipulated to be called HTTP secure because TLS. TLS SSL, this seems confusing. Really simple. At some point, the SSL spec got renamed, it evolved. It's now called TLS, Transport Layer Security. It's essentially the same thing. It's just a newer revision of that spec. So when you hear things like SSL certificate in a TLS context, they're the same thing, right? So when we establish communication between a client and a server, we start by setting up a TCP connection. If it's going to be a secure connection, we're going to upgrade that TCP connection to TLS. So it's at that TCP layer. We're basically creating a pipe, and then we can throw whatever protocol we're using, for example, HTTP, through that pipe. So I can send a packet. It's completely unintelligible to anybody who kind of intercepts that encrypted packet, but the receiver, who I'm supposed to be talking to, can decrypt it. So we've got an encrypted connection between the two. So I have some code. Of course I have some code. I have a very basic, is that big enough? Can you all see that okay? Yeah, great. So I have a very simple server. It's got a very, very simple handler function, which is going to return a message. And my TLS config has some commented out code. There's nothing there at the minute. And all I've said is I'm going to serve on address on port 8080. And I also have a client. My client is also very, very simple. It's going to make a request to Liz server that I've got an entry in my etc hosts file on my laptop so that Liz server resolves to my laptop. And it's just going to make that request, again, completely vanilla, empty TLS config and transport. So at the moment, this code does nothing very sophisticated. It's the simplest web server in the world. But let's just check that it works. So again, is that big enough? Yeah, great. So we'll run the server, and then we run the client. And yay, we can send a web request. Okay. So what happens if we send to a different port? My server is still running. When I run my client and I hit the wrong port, I get back connection refused. Now I'm pointing it out now, we haven't got any TLS going on, no security here going on at all. When you hit connection refused, when you see that message, it means you are basically addressing a port that is not open. The server is not listening on that port. It's also possible that you're going to see that message if the server ran out of resources to respond on that port, but forget that. When you see connection refused, nothing to do with the security. It just says the other end is not listening. It's probably the wrong port that you're making that call on. Okay. This is kind of the flow that happens. We start with establishing the TCP connection. Don't worry about the whole flow. We're not going to go through the whole thing. The top bit, if we were addressing the wrong port, we wouldn't even get back. We would go no further. We wouldn't establish this TCP. This would come back failed. If we decide we want to do TLS, or rather if the client is going to attempt to set up TLS, it goes through this TLS handshake flow, which starts with a hello saying which server it wants to talk to. Now, it goes through this whole flow. The point of me showing you this is that these kind of bold black things are callbacks that you can set up in the standard Go TLS package. And they're there so that you can fill in a certificate or take a look at the peer certificate you've received. For my purposes, I'm using those callbacks to put in some kind of debugging information so we can look at what's happening as we go through these flows, and we can see the certificates as they kind of get passed from one end to the other. Okay, so let's say that we want to make a secure connection, and we are going to call HTTPS. Under the covers, that's going to use TLS dial rather than just net.dial. And I'm just going to uncomment these. These are the callbacks that I just talked about. Yes, they do call. I've got some functions in a utils package. Please don't judge me. I know that is exactly what Kat said not to do, but this is just demo code, right? If you want to take a look at what those callbacks are doing, it's on GitHub, and I'll be sharing the link later. But for now, just it's just printing out some interesting information as we go along. Going to uncomment these ones as well. Okay. So if my client requests TLS, I need to just start that server again. Oops, what's going on? There we go. My client requests a secure connection and the server isn't planning to respond with TLS, my client is going to reject that. So I need to set up my server to say we're going to use TLS. And as I'm sure you probably all know, we do that by using listen and serve TLS. And this function requires me to pass in a certificate file and a key file. So I'm just going to leave those blank for a second, and this seems like a good time to talk about keys and certificates. There's going to be a ton of this stuff that I'm sure a lot of you know, but I just want to make sure we are all completely on the same page here. So this all uses public-private key pairs, public-private key encryption. So you generate these pairs of keys. I might keep a private key, and I can give you all a copy of a public key, and then you can send me encrypted messages that only I can read because I have my private key. So the public key is how somebody sends, or how they use, that's what's used to encrypt a message. But we can also use these public-private keys for signing messages. You have a private key, and you have some message that you want to send, and you do essentially like a hash function with the message and that private key, and you get out a signature. You can send the message and the signature to somebody who has the public key, and they can use that public key to verify that the hash, if you like, the signature, matches the message. They've got the signature and the message, and if they match, all is good. It also gives you a mechanism for establishing identity, because if I've given you a public key and you know that it's my public key, then when I give you a message and I've signed it with my private key, if you can validate that signature, you know that only I, as the owner of that private key, can have sent it to you. So long as you know that it was me who gave you that public key in the first place, you know my identity, you know who I am. Except for the fact that you don't really know who I am at all, because I've just come on here and, well, Paul said that I'm Liz, but you don't really know that I'm Liz. Why should you believe me? We need some kind of trusted authority that will validate that when I say I'm Liz, I really am. And that is what a certificate authority is. You might come across the term X509. It's just the name of the standard that defines what certificates look like. And they're not actually as complicated as, kind of go, oh, X509 certificate sounds really complicated. But if you think of it as it's got the identity that we're going to establish, so in my example, it's Liz server. It's got the public key that we're going to associate with that identity. And then it's been signed by somebody that we trust, a certificate authority. And it may also have some date range that it's valid for. So the certificate becomes the way that we share that public key. I've said, I'm giving you all this public key. I actually give you a certificate containing the public key and my identity and a signature from somebody that you trust. Inside those X509 certificates, there is a field called common name. Now, I discovered at GopherCon about 24 hours before I was doing this talk, that common name has been deprecated for 18 years. And although you will see it in use, it's increasingly being ignored. There are some ambiguities in how common name can kind of be resolved to a domain. So instead, you should be using a thing called subject alternative names, which also allows you to have multiple kind of aliases for the same identity. And as Go programmers, if you want to kind of get ahead of the curve, you can set this Go debug flag to actually ignore the common name field altogether. This is going to become the future standard behavior eventually. It's currently, so if you have a certificate and, well, the Chrome browser will already ignore common name. It requires you to use subject alternative names. So this is, although it's been deprecated for 18 years and we've been carrying on using it regardless, all the certificate authorities, all the trusted ones that you've heard of, they're all using subject alternative names. It's really up to the person validating the certificate to ignore the common name, really. So, how do we actually go about creating these keys and creating these certificates? There are lots of tools available. There are lots of sources for them. You can, if you're publishing something on the public internet, you want a certificate that is going to be trusted by kind of everybody. And there are these well-known certificate authorities, people like Let's Encrypt or VeriSign or whoever else, who will give you or sell you a certificate that you can use to validate that you own something on the public internet. To get one of those certificates, you create a thing called a signing request, and that has information about your identity that you then pass to the certificate authority. The certificate authority, in order to retain some kind of credibility, has to actually check that you really are who you say you are. So that's often done by getting you to do something like maybe change a DNS record so that you're proving that you are really in control of that domain that you're asking for a certificate for. And then once you've made the change that they've requested, they check that it's in place, they now know that you control that domain and they can issue a certificate for you. Which is great but useless if you are building like if you want certificates for internal microservices. That is absolutely no use to you because you're not going to publish all those domains. This could be private. So if you want certificates that you can use in your private system, in your kind of distributed components, you need to generate certificates yourself. And you might well choose to use one of a variety of different tools out there. OpenSSL, when I was first writing this talk, I was going to do the demos using OpenSSL, which is this pretty common and comprehensive toolkit that you can use for all sorts of encryption things, including generating keys and certificates. But it turns out that if you want to use the subject alternative names and not have common names, you kind of have to, it's not the default behavior. It can be done with OpenSSL, but it wasn't lending itself to doing it in a quick demo. So I decided not to use OpenSSL. There is also Cloudflare's SSL package, CFSSL. That's a pretty comprehensive toolkit and does support the SANs pretty easily. There is a thing called MakeCert that is really good if you're doing local development. It installs itself as a certificate authority on your machine and installs itself into things like your browser, so you can browse to a site or something that's under development on your laptop, and your browser will trust the certificate. And then finally, there's a really, really simple thing called mini-CA, which is what I'm going to use. And this is really nice. If you are going to do certificate generation programmatically, which you might do if you're doing a distributed system, mini-CA is a really nice source because it's like 300 lines of code, so it's not hard to read and see how these keys and certificates are actually generated. Okay, so if you recall, we need a key and a certificate for the server. So I have a version of, I have mini-CA installed, and when you install it, it generates a key and a certificate for itself. And then generating a key and certificate pair is as simple as doing this. So I want a certificate for my Liz server domain. That creates a directory, and if I look inside it, I will find a certificate. So that's mini-CA signed a certificate with the identity of Liz server. And inside that certificate, there's a public key, and the corresponding private key is this key.pem file. We could take a look at that with OpenSSL. Actually, before I do that, let's just look at the files themselves. So if we just look at the certificate file, it does at least tell us what it is. It's got human readable form text that tells us what's inside it. And we can do the same thing for the key, and it's going to tell us that it's a private key. So that's kind of useful. It seems like a good time to just talk briefly about the file extensions. So those .pem files with those human readable kind of header and footers are, well, they're called PEM because privacy enhanced electronic mail is exactly what we're doing. But inside that is base 64 encoding of a binary ASN1 format called DER. You could also find, and you commonly will find, certificates and keys in that DER format. I don't really know what the cause and effect is here, but if you have those binary files, there isn't really a way as a human you could just look at them to find out that they are a certificate or a key, so they're often given an extension like certificate or key or what have you to distinguish between them. I certainly feel like I'm increasingly seeing the PEM format files anyway. You can also use OpenSSL to take a look at what's inside these certificates. So we want to, text. Let's have a look at the Liz server certificate file, and that should do it, right. And we can see some interesting information in here. We can see that the issuer is my mini CA. We can see some validity. It does have the common name field, this CN field, but don't worry because down here we've also got the subject alternative name. So if it were, for example, the Chrome browser or the Go standard library with that debug flag turned on, it would ignore the CN up here, and it would just look at this subject alternative names down here. And we've got the public key here. So that's the core components of what's in the certificate. The identity in the form of a SAN, the public key, and information about who signed it. Oh, and down here is the actual signature. Okay, so let's copy those files to my server directory. Okay, and we'll go back to the server directory. Check they're there, great. So in my server, now I would traditionally put those certificate files and key files in here in listen and serve TLS, but because I've got these callbacks, I'm actually going to put them in here. It does do the same thing, as you can verify for yourself should you want to look at my Git repo. Okay, so hopefully that will allow my server to use a certificate for a TLS connection. Let's find out. So we run the server, and we make the request from the client. Okay, so this is my callback in action. It has received the hello message from the client, and the client is asking for Liz server, and so my server tells me what certificate it's going to send back, and the certificate is that one we just looked at. It identifies as Liz server, and it says it was signed by mini CA. Great. So it sends that back, and we get an error message. Now, if you're like me and prone to sort of slightly panic, what's wrong with it? It's a broken certificate. And you kind of have to exercise a little bit of patience and look a bit further back, and it says remote error. It's not this end that's complaining about the certificate. It's the client that's complaining about the certificate. And that gives us a much more sensible and helpful error message, which is that the certificate was signed by somebody that the client doesn't know about. It's a certificate authority that the client does not trust, and therefore it doesn't trust the certificate. So when you see remote error, well, just make sure you read the error message carefully enough to spot that it says remote error, because that can give you some clues that are stronger and more informative than bad certificate. Okay. My client doesn't trust that certificate. We have a couple of options. One of them is to do insecure skip verify. And that is also known as the -K option on curl. I'm sure you've used it. And if we do that, we get the certificate, the hello request asking for a certificate. And when we send that certificate back, what actually happens is the client goes, great, I've got a certificate. Doesn't look at it, just checks that there's a certificate there, but doesn't look at the identity inside that certificate. So we have actually got something useful here. We have got encryption set up between the client and server. What we haven't done is establish that the connection is to the server we intended it to be. But maybe it's useful for some. Okay, what we really want to do is not do that, but instead we want the client to know about the certificate that the certificate authority that signed the certificate. And we do that with root CAs in the TLS config. I'm going to call that CP. Right, so CP is an X509 certificate pool. This is a set of certificates that we're going to trust as certificate authorities. So if you think of a certificate as telling us about an identity, this is also where we maybe want to mention the word self-signed certificate. Maybe that certificate has been signed by itself or signed by the subject. So long as that certificate is in this trusted certificate pool, the client will trust it. Now, we have a couple of options here. We have X509. We can either start with a new certificate pool, or we could start with the system certificate pool. So this is kind of set of certificates that have been built in, and it's going to be all those let's encrypts and verisigns and what have you that we probably all trust. So we start with that certificate pool. We read a file from, we want to read mini-CA's certificate, which is here, mini-CA. That's mini-CA's own certificate file. This could return an error, but I am going to ignore it. And then we can, let's get the autocomplete. Append, hopefully. Oh, it doesn't like something here. What doesn't it like? Ah. Yeah. There we go. Append certificates from a PEM format file. So I can just pass in that data. So I've got the system certificates, and I'm adding mini-CA's certificate, and then I'm saying these are the whole set of certificates that you should trust. Certificate authorities that you should trust. Okay, so the server gets a hello asking for Liz server, and it sends back exactly the same certificate that it did before. And on the client side, it's been able to verify that certificate now. It received it, it's signed by mini-CA, it says mini-CA itself was self-signed. The fact that it even called this callback tells me that it did verify that certificate, and the client is happy to proceed. So we have set up a TLS connection. We have a secure connection in which the client knows or has been able to confirm the identity of the server. But at this point, the server has no idea about the identity of the client. So that brings us on to mutually authenticated TLS. Now, this is kind of what you want to set up if you have peer components that are, for example, in a distributed system, and they both need to validate each other's identity, and they're both going to use certificates to do so. Even though they're kind of in a peer relationship, it's still we're still going to talk about clients and servers. So it's a client who initiates the TCP connection, and it's the client that can say, I want to upgrade that to a TLS connection. But what we can do at the server side is we can say, I also want to authenticate the client. And in the Go TLS package, there are lots of different options here. I'm going to go for the strongest one, which is require and verify a client certificate. Okay. Oops. Wrong way. Right. So, run my server again, run my client. So, the client sends TLS hello to Liz server. Liz server has a certificate that it sends back. And the client is perfectly happy with that certificate. The next step is that the server sends a certificate request to the client. And at this point, the client doesn't have a certificate, so it's just basically saying, I don't have one. And we get that bad certificate error again. But also, it is helpfully identified as a remote error, so we can go back to the server and see a more explicit message that tells us the client didn't provide a certificate. Okay, so we need to go back to the certificate authority and create a certificate, which we will do with a mini CA again. What should we call this? London? Seems all right, doesn't it? And now we've got a London certificate and key file, which I'm going to copy to my client directory. Oops. That's not what I meant. I'll get this right in a second. We're copying the contents of London to the client directory. Go back to the client directory, check that I didn't screw that up completely. No, there it is. Good. So now we need to have the client read in that certificate. And again, I'm doing that in this callback. There are other options. There's a certificates field here. We could specify the certificate here. I'm just going to do it in a callback. PM and the key. Okay. So we'll run that again. And as before, the client sends a request for a certificate. The server sends back a certificate. The client is happy with it. The server also requests a certificate from the client. And this time, the client has a certificate in its hand saying, I am London. I'm going to send that one back. And we get that at the server end. Again, at the client end, a not terribly helpful message about bad certificate. But on the server end, it's exactly what we had before. The server doesn't trust the certificate authority that signed that certificate, which kind of almost seems a bit ironic because it's got a certificate from that certificate authority itself, but still, it doesn't trust it. So we have to explicitly tell the server to trust that certificate authority. We can copy exactly the same code as we used on the client side, except here it's called client CAs rather than root CAs. Now, I think this is another area for a bit of confusion if you are programming in Go. This Tls conflict structure contains all the configuration, whether you are a client or a server, and some of those fields are kind of common between the two, and some of them, like this example, if you're on the server side, you have to use client CAs, and if you're on the client side, you use root CAs. The comments are kind of helpful-ish, but you have to read them pretty carefully. Okay, so hopefully Right. The initial flow is exactly as before. We're going to send a certificate from the client back to the server. And this time, the server has been able to verify it, and it trusted it. And therefore, we can send a message that has been, well, it's on a secure connection in which both ends know about the identity, and it's encrypted between the two. We have successfully set up a mutual TLS tunnel between the two. So, a few things to take away from this talk. In order to establish your identity, you're going to need a private key so that you can decrypt messages sent to you, and you're going to need a certificate that you can give out that contains a corresponding public key, and whoever signs that certificate has to be trusted by whoever it is who's going to read that certificate. File extensions can be really confusing and they're used inconsistently. PEM format files do at least give you a sort of human readable way of quickly seeing what kind of contents they have. You can also use OpenSSL to actually get inside both PEM format and binary format files. And then finally, the error messages that you see. If you ever see connection refused, you're probably addressing the wrong port. If you see certificate signed by an unknown authority, it means you've received a certificate, but you don't trust the CA that signed it. So if you're in that situation, you might want to use something like OpenSSL to examine the certificate and find out who did sign it. Was that a certificate authority you intended to trust? And then finally, and the thing that I have to remember more than anything, read the error message carefully so that if it's a remote error, you spot that and you know that it's the other end that's going to give you a more informative message. So hopefully, understanding what those error messages are will stop you from getting confused and in a bit of a panic when your certificates don't work. If you want to check out the code and see what I did with those callbacks, it's on my GitHub there. Also just going to mention, there was just referring to that, what did you call it, conundrum, the quiz, conundrum? There was a really good talk at GopherCon, I think it was by John Bodner, and it was something like Go says what, and it had a whole load of things like that conundrum, and it was really, really good, so I definitely recommend that talk. We have some stickers, we have some stickers also from some open source projects that we do at Aqua, KubeBench, which will validate your Kubernetes configuration, and Microscanner, which I mentioned last time I spoke at this meetup, for scanning your containers. I hope you're all using it. Okay, with that, hopefully you will never be confused about TLS, certificates, keys, or anything like that again, and I will take any questions. Thank you. Hopefully there aren't any questions, because it was all really clear. No, there could be questions. There might not be questions. There's a question. Yes.
Well, maybe a bit out of scope, but you mentioned container security at the beginning. So I was wondering if you would recommend encrypting traffic inside a private network, so containers talking to other containers inside a private network.
Okay. I would say generally yes, because there's this principle called defense in depth, which is the idea that should one layer of defense be broken through, another thing can protect you. So if maybe you've got a VPC and all your components are inside that VPC and you really don't think anything can get into that network, so you might think, oh, I don't need to encrypt traffic on that network. But suppose there is a vulnerability inside a container that's running inside that network, which does happen, and that vulnerability might, if you've got encrypted traffic, that will restrict some of the things that vulnerability would be able to do. So, yeah, I would say, why not? Yeah. What's the reason not to, really? Oh, loads of questions. Oh. Can I just say, I'm so happy I don't ever have to catch that. I'd never ask a question because I'd be too scared of catching it.
Sure. It's regarding MTLS. So imagine we want to be really secure even in a private network, and we have three services talking to each other, A, B, and C.
Uh-huh.
Now, A is allowed to talk to B, but A and C, we don't want them to trust each other or have any communication with each other. So we try to solve the problem using this certificate. Now there should be a tool somewhere, some repository, who recognizes each one of those and knows about these connections. So go and define these like trusts between them. And I imagine doing this by hand is going to be very complicated. Do you know, or anybody knows any tool that is providing this?
Right. I think you're right. It could be done like that. I've not personally heard of people doing it that way, but there are other techniques that you can use to stop, or to either stop services from talking to each other, or to kind of whitelist so that only certain services can talk to other services. Istio is a cloud native kind of project. It's not under the CNCF, but it's in that kind of Kubernetes world. One of the things that it does is allow you to configure specifically which services are allowed to talk to which other services. There are also commercial products like, for example, Aqua, which will enable you to restrict what containers are allowed to talk to what other containers, which would solve a similar problem. Thank you for letting me pitch my product.
So it seems like when you're like writing Go services using TLS, and if you have to debug them, is the general advice write your own callbacks and inspect the certificates, or is there some way of like collectively auditing certificates used by all your Go services en masse and like debugging certificates in production?
Right. So if I just use those callbacks, to kind of see where those errors are happening in the flow. You don't have to use callbacks at all, and you will see those error messages. It's just a little bit easier.
So, sorry, if the advice is like so, inspect the certificate you're receiving and see who signed it, is there some kind of like general wisdom that you see the certificates that your services are receiving?
So I guess I was thinking about a scenario that I found myself in a few months ago, where I was trying to set up some certificates between some components, and I tried to follow not Kelsey's instructions. It was actually a different thing, but similar kind of hundreds of lines of instructions, and I was left with all these files, and I'm like, I don't really know what they're all for. And I was getting these messages, and it's a long-winded way of going like, this needs to be clearer. I shall write this talk. I shall understand it and then write this talk. But one of the things that I found myself thinking was, this is telling me it's a bad certificate, and, it's telling me, then you kind of go, it's not a bad certificate, it's an untrusted certificate. Why is it untrusted? Why didn't the certificate authority match what I expected? And it came down to I hadn't added, so I think it was something like etcd, and you can pass in a set of certificate authority files that you are going to trust. It's a configuration. I think if you're in this world, or in the world of these kind of distributed infrastructure tools, you're quite likely to not be doing it programmatically. You're quite likely to be doing it by configuration, but understanding how the flow works means it's easier to understand those messages, I think. So am I saying, I'm definitely not saying try and put callbacks in to debug what's going on unless you get really desperate. I guess I'm saying one of the tools at your disposal for debugging this kind of problem is using things like OpenSSL to check that the certificate, because if you look at the PEM format, you've no idea, like, unless you're really, really careful about what you called the files, you can very quickly end up with these PEM format files. You're like, I don't remember, was this the one I did for this end or for that end? And you can use those tools to inspect.
So like, maybe something cool to add would be some kind of integration with like open tracing to just kind of like dump the raw
Yeah, I think there might well be some tooling that does that kind of thing. That rings a bell of something that I was going to look into and forgot.